In our last class, we discussed about organomercurals, isn't it? So organomercuric compounds. So today we will discuss about one more organometallic compounds that is what is called as okay. Let's give an entry. Right. So today we will discuss about one organometallic reagent. Okay. The use of organometallic, more particularly organoselenium compound in organic synthesis. Silicon, okay, is a metal. More particularly, it's a milder metal. I think you are aware about the silicon tubes, okay, and silicon oil, okay, and below the carbon, more particularly the silicon is situated below the carbon in periodic table. That means it belongs to a carbon family. So that means valency also of silicon is 4 only. Similarity between the silicon and carbon is both having a tetrahedral geometry. The difference between the silicon and carbon. Silicon forms stronger single bond with the electronegative elements than carbon. So here I am giving a data about carbon and other atoms bond energy. Similar to that, I am also giving a silicon and other elements bond energy. You can just compare. So look here, carbon oxygen bond energy is around 336 kilojoules per mole. Carbon and fluorine, it's around 485. Carbon and chlorine, it's around 327. Carbon and bromine, it's around 285. Carbon and iodine, it's around 213. So what indicates? It indicates that the bond between the carbon and fluoride is very strong in this data. So with this, I will go to the next slide. Next slide will give you the information about the bond angles in silicon and other elements. So look here. Silicon and oxygen is around 368 kilojoules per mole. Silicon and fluoride, you can observe that 582. So what it means? It means that very strong bond between the silicon and fluoride. And you can also observe, look here, silicon, oxygen, 368. The bond energy is more. You can just compare here, silicon and carbon, 290. So what it means? So just by looking into the data, you can say that the bond between the carbon and silicon is weak. The bond between the silicon and oxygen is more. So that is the reason the bond formation between the silicon and oxygen favors the formation, whereas the cleavage is possible between the silicon and carbon. So based on this parameter, several reactions we were going to study. So in addition to this, you can also observe the bond energy between the silicon and fluoride, 582, silicon and chlorine, 391, silicon and bromine, 310, silicon and iodide, 234, silicon and carbon, it's around 290. Silicon forms weaker bond with the electropositive elements. Silicon forms weaker bond with electropositive elements with respect to carbon. For example, silicon hydrogen bond is weaker bond than CH. Carbon forms single as well as multiple bonds, whereas silicon forms mainly a single bond. Silicon carbon bond is strong enough, for example, a trialkyl silyl is a strong enough. Survive in the chemical transformation, but at the same time weaker enough to be cleaved during the reaction. So what we can say that silicon as a low electronegative. Silicon has low electronegative, that is 1.8 than 2.5. So that is 2.5 is what is called silicon carbide. Silicon carbide means silicon carbon bond. So silicon carbon bond is polar and carbon bears positive charge. So overall, what you can observe from this, uh, carbon attains a delta positive. Silicon attains a delta negative. So that I will show it to you now. So look here. Silicon forms a positive charge, carbon forms a negative charge. Hence, silicon is attacked by nucleophiles. So because of this delta negative and delta positive, uh, because of the electronegativity difference between the carbon and silicon, silicon will be attacked by nucleophiles. The nucleophile may be a O minus, nucleophile may be a Cl minus, Cl or Br or iodo or fluoro. Okay, overall, silicon is attacked by nucleophiles. So with this information, I will go for a preparation, okay, preparation or synthesis of organosilicon compounds. So more particularly, silyl compounds. Selenium compounds is different, Se. Silicon is Si. Don't get confused with the selenium compound and silyl compound. Silyl is Si. Silicon and selenium is Se. Silicon is Si. That is the difference you need should aware about it. So, if you want to prepare a trimethyl silyl chloride, so the reactants are silyl tetrachloride. Silyl tetrachloride is a reactant. So that tetrachlorosilane react with the methyl magnesium chloride. So what is the product obtained? The product obtained is trimethyl silyl chloride. I will explain in the later stage what are the advantages of trialkyl silyl halides. Okay, trialkyl silyl halide is a general silyl compound. This is a particular example. So the obtained silyl chloride, so when it is treated with lithium, okay, so there will be what lithium iodide. So what is happening here? Iodide is exchanged. That means iodide will go and form a bond with the silyl. Chlorine will go and form a bond with lithium. So let's give an entry. Right. So here it's only the halide exchange. Trimethyl silyl chloride is converted into trimethyl silyl iodide. So what is the name of this compound? Hexamethyl. This is trimethyl. This is trimethyl. Hexamethyl di. Two silyl compound is there. No, that is the reason. Disilane is the name of this compound. So hexamethyl disilane, when it is treated with iodine, it gives trimethyl silyl iodide. Okay, this is one silyl compound, more particularly organosilyl compounds. So these are the methods of preparation of silyl compounds. Of course, few more are there. I will go to the next slide. So look here, I am taking this group is called allyl group. Allyl means double bond CH2 containing one is called allyl group. So this is magnesium chloride. So what we can say that allyl magnesium chloride. This allyl magnesium chloride, when it is treated with the trimethylsilyl chloride, so you know that this is a nucleophile. The bond between the carbon and magnesium, or this bond pair is attacking a silicon. Otherwise, what we can say that there will be a new bond formation between this carbon and this selenium. So what is going out? So magnesium chloride, MgCl and this Cl will going out. So what is the product form? So this double bond CH2 is called allylic, and this is silane because Si is between the two carbons. This is one carbon, this is another carbon. So silane, just like alkane. So here I am taking one more trimethyl silyl chloride. This is a reactant. Of course, this is also a reactant. So what is the name of this compound? It's a vinyl group. This double bond group is called vinyl. Or otherwise we can also say that alkenyl. Alkenyl, ALKENYL, alkenyl lithium. So alkenyl lithium, so here this is the nucleophilic in nature. There will be a new bond formation between this carbon and this silyl group. So the product is this. What is the living group? Lithium and Cl is the living group. So here I have written as a iodide. You make it as Cl. Then what is the name of this compound? Alkenyl, otherwise vinyl. Vinyl alkyl silane. Vinyl alkyl silane is the product. It is also possible to prepare trialkyl silyl cyanide. Trialkyl silyl cyanide. How one can prepare? With the trimethyl silyl chloride. Trimethyl silyl chloride, when it is react with sodium cyanide, it gives trimethyl silyl cyanide. This is about preparation. So maybe in the next slide, we will look into the reactions. So two types of reactions are possible. One type of reaction is used as a nucleophilic reagent. Used as a, that means trimethylsilyl compounds used as a nucleophilic reagent in O carbon, means oxycarbon bond cleavage. Oxycarbon bond cleavage, where and all you can find? You can find in ethers, you can find in epoxides, you can find in esters, you can find in lactones, you can find in carbamates. Okay, so that means this silyl compounds cleaves the bond between the oxygen and carbon. So this is an ether. So ether, this will be the general structure of ether. So you know that there is a lone pair present on the oxygen. Of course, these electrons are called bond pair. So what will happen? Lone pair or the bond pair can attack this silyl compound. Why it is attacking? Because the formation of oxygen and silyl bond formation easy, and the formed bond is very strong. So because of that, there will be a new bond formation between this oxygen and this silyl. So what it means? Two molecule of trialkyl silyl halide react with the ether, so giving rise to two alkyl halides. If the R1 or R2 is different, you will get a different alkyl halides. Of course, this is a byproduct. Okay, so this is about the general reaction. So now let's look into the mechanism, more particularly the ether cleavage by using trimethyl silyl chloride. So with this, I will go to the next slide. So look here, this is the mechanism. The lone pair or the bond pair can attack silyl bond. It means that there will be a new bond formation between the oxygen and silyl. Iodine will go out. So it won't go as such. What it will do, it will pick up this R group. Why it is picking up? Because once there is a lone pair or bond pair is involved in the bond formation, when oxygen attains a positive charge, to neutralize that, this bond pair is coming over. When this bond pair is going, R1 become a positive charge. If R1 is positive charge, will be the negative charge. There will be a new bond formation between the R1 and I. So that is how a byproduct is going out and the product is formed like this. So now also what you can observe, there is a oxygen, there is a silyl, there is a R2. So this moiety, again the lone pair present on the oxygen can react with selenium, one more equivalent of trimethyl silyl halide, so forming an intermediate like this. Once there is a bond formation between the oxygen and silyl, oxygen attains a positive charge, then this bond pair comes out and sits as lone pair. And that means R2 along with the I, means iodide, goes out as a alkyl halide. So this is about the mechanism, more particularly ether cleavage mechanism. So here I am talking about the order. So tertiary group, okay, takes the priority in the cleavage. So that means if R1 is the tertiary group, so that will go out as a tertiary iodide. If R1 is a benzyl group, that will also go out as a alkyl halide. If R1 is a halcyl group, that will also goes out as a allyl alcohol, allyl halide. So what I means that, so these three takes the equal priority. Equal means equal, approximately equal. Tertiary, benzyl, allyl, approximately equal. Otherwise, allyl takes the priority compared to the methyl group. Methyl takes the priority compared to the secondary. Secondary takes the priority compared to the primary. So this is the order. So here I am taking one example. Name of this compound is called tetrahydrofuran. Furan is an aromatic compound. Furan contains two double bonds. Those two double bonds is hydrogenated, means a tetrahydrofuran is coming. So tetrahydrofuran is a colorless liquid having a boiling point around 6 to 5 degrees centigrade. It's a ether, okay? I boiling ether, because diethyl ether is having a boiling point around 35 degree. So that means ether evaporates at room temperature. Of course, Tetrahydrofuran also evaporates at room temperature, but it is less compared to the diethyl ether. So this ether, when it is treated with the trialkyl silyl iodide, what will happen? The lone pair present at the oxygen forms a new bond with the silyl, and iodine, what it will do? So if there is a lone pair involvement in a new bond formation, oxygen attains a positive charge, then this bond pair convert as a lone pair, then this carbon attains a positive, that carbon attacked by I minus, so that is how the bond formation. A iodo alkyl silyl ether. Iodo alkyl silyl ether. Again, the lone pair can attack one more equivalent of trimethylsilane and forming a diiodoalkane, and this is one byproduct. So this is about the ether cleavage. So with this, I will go to the next slide. Next slide will give you the information about epoxides. So what is epoxide? Oxyray, isn't it? This is an example of an example of epoxide. Oxygen is in the cyclic form. So the lone pair can react with the silyl. It means that there will be a new bond formation between the oxygen and silyl. So once there is a new bond formation between the oxygen and silyl, then oxygen attains a positive charge. That's what I have written here. At this stage, if we are using a more quantity of trimethylsilyl halide, so what it will do? The lone, again, this bond pair, once there is a positive charge on the oxygen, this bond pair will convert as a lone pair. Then this carbon attains a positive charge. That time I minus will form a bond with this carbon. So that is how a compound is obtained. So at this stage, if we are using a more quantity of trimethylsilyl halide, so there will be a new bond formation between this oxygen and this silyl. Okay, so that means once there is a new bond formation between this oxygen and this silyl, since there is a involvement of lone pair in the bond formation, then this bond pair is moved towards oxygen, then this I minus will form a bond with this carbon. So that is how diiodoalkane is obtained. This diiodo elimination, how it is eliminated? This bond pair is come over here, this bond pair, this I minus picks up I. So removal of I giving a alkene. So what it means? It means that epoxides on reaction with the trimethylsilyl gives alkene as the product. Ethers on reaction with the trimethylsilyl gives iodoalkanes. This is the thing you need to remember. Okay. So with this, I will go to the next slide. So ester method. The ester is treated with the reagent. The ester is treated with the reagent to form an initial oxonium ion. So this is only oxonium ion. So that means if ester is the lone pair present on the oxygen, can form a bond with silica. So that is how the intermediate like this. Once there is an intermediate like this, what it will do? There is a positive charge. This is only called oxonium ion intermediate. Since there is a positive charge on the oxygen, the bond pair between the oxygen and alkyl will turn out as a lone pair. That means R2 attains a positive charge. This R2 positive charge is attacked by I minus, there will be a formation of alkyl halide. So this on hydrolysis, okay, in presence of water, silyl esters, the obtained compounds are called silyl esters, giving rise to carboxylic acids. So this will go out as a living group, and this is called lactone. So lactone, what is the difference between the ester and lactone? So ester is a open, lactone will be the cyclic ester. Cyclic esters are called lactones. So lactone also contains oxygen. Lone pair also is there on the oxygen. That lone pair form a bond with silyl. So once there is a bond formation between the oxygen and silyl, oxygen attains a positive charge, then this bond pair try to move towards oxygen. That time I minus will attack this carbon. So that is how iodo-silyl ester. This is iodo-silyl ester is this. Iodo-silyl ester is obtained. So what it means? So esters on reaction with silyl halide gives carboxylic acids. Lactones on reaction with the trimethyl silyl halide gives iodo-silyl esters. This is about esters. So with this, I will go to the next slide. So next slide is about carbamates. C-A-R-B-O-M. This is not N, it is M. Carbamates. So carbamates means NCO2 ET is called carbamates. So this is a carbamate. This is a carbamate. If R2, what is called R3 is an ethyl, methyl, propyl, whatever it is, it's a carbamate structure. So what will happen? Carbamate, when it is treated with the trimethylsilyl halide, the lone pair present on this oxygen form a bond with the silyl. So it forms an intermediate like this. This intermediate having a positive charge on oxygen. So these are highly unstable. So that is the reason the lone pair means the bond pair between the oxygen and R2, okay, convert as a lone pair. Then R3 attains a positive charge. That R3 is attacked by I minus, so forming a alkyl halide with the product called silyl ester, silyl carbamates. So now it's a carbamate. This is the silyl carbamate. So this on hydrolysis, what will happen? Breakage here, forming a carbamic acid. So this carbamic acid on heating, there will be a removal of carbon dioxide. So what is the product obtained? The product obtained is what is called as a secondary amine. So what it means? It means that carbamates on reaction with the trimethylsilyl iodide followed by hydrolysis gives rise to secondary amine. So we discussed that what happens when an silyl halide is treated with ether, treated with epoxide, treated with ester, treated with carbamate. So with this, I will go to the next slide. So next slide, I think you are aware about the acetal and ketol. So what is the ketol? What is the acetal? Ketone, when it is treated with ethanol in presence of its place. Okay, it is nothing but a ketone protection, acetone, aldehyde protection. If aldehyde is protected by using alcohol in presence of HCl, the obtained product is called acetal. If the ketone is protected by using alcohol in presence of HCl, the obtained product is ketol. So acetal or ketol, when it is treated, acetal or ketol is nothing but ethers. So here the cleavage of ether policy follows. So that means there will be a new bond formation between the oxygen and silyl. So there it is forming like this. I minus attack the carbon which is attached to a oxygen. Okay, and this bond pair going. So that is how iodo-silyl ether is the product when acetal is treated with trimethyl silyl. So here it's a ketal, okay, because two substituents are there. This is one substituent, it is a acetal. So ketal, when it is treated with trialkyl silyl iodide, so that means there will be a new bond formation between this oxygen and this silyl. Okay, that is how a intermediate is formed like this. At this stage, since there is a positive charge on the oxygen, this bond pair move towards that. Then R1 attains a positive charge that was attacked by I minus. So that is how giving rise to silyl ether. Of course, silyl ether intermediate is obtained. So this one react with another equivalent of trialkyl silyl iodide. So that means there will be a new bond formation between this oxygen and this silyl. So what will happen? So it will form a disilyl ether. This on hydrolysis giving rise to ketone. So what it means? Acetal or ketol on reaction with the trimethyl silyl giving rise to aldehyde or ketone. So in the case of acetal, iodo-silyl ether is the product. In the case of ketol, a ketone is the product. So with this, I will go to the next slide. So next is about the another type of reaction that is used in the synthesis of alkene. So that means trimethyl silyl chlorides are used in the synthesis of alkene. Synthesis we also call it as a olefins. So here there is a name reaction called Peterson olefination or olefination reactions. So definitely you can have one or two questions on this Peterson olefination, maybe for the 4 marks question or maybe for the 2 marks question. What is Peterson olefination? Okay, explain Peterson olefination with an example. So here in many reactions, this is called a trimethyl silyl group act like a proton. So just as a acidic proton are replaced by bases, silicon is readily removed by hard nucleophiles. So what are the nucleophiles? Nucleophile may be a fluorine, bromine, iodine, and alkoxy. Okay. So what it means? It means that the bond formation of silicon and fluorine is strong. That is the reason silyl will go out as a living group. The bond formation between the oxygen and the silyl is more. That is the reason it will go out. So what is happening here? So when alkyl silyl compounds having a beta hydroxy. So this is alpha, this is beta. So what it means? Beta hydroxy silyl compounds undergo elimination reaction in presence of acid. So giving rise to olefin or alkene. This reaction is called Peterson reaction. So what you need to write? Beta hydroxy containing silyl compounds. Beta hydroxy containing silyl compounds undergo elimination reaction in presence of H plus, so giving rise to alkane. This type of reactions are called Peterson olefination reactions. So what is exactly happening here? The lone pair present on the oxygen can form a bond with the proton source. Here the proton source is hydrofluoric acid. HF means hydrofluoric acid. So there will be a positive charge formation like this. At this time, this F minus is a leaving group, no? That will form a bond with silicon. If F minus is forming a bond with silicon, then this bond pair is coming over here, this will go out. That is how a olefin is obtained. Here the olefin is styrene. I think you are aware about styrene butadiene polymers. So this is how a styrene is prepared. So with this, I think you are aware about what is called as, I will take one more example. Okay, I think you are, okay, I will go to the next slide. So you are aware about, look here, this is one example. So I think what is happening here, this is a hydroxy group and this is a silyl group. So adjacent to silyl, this is alpha, this is beta. That means beta hydroxy silyl compound. This hydroxy can take a proton from the acid source, form a hydronium ion. Once there is a formation of hydronium ion, this bond pair is coming over here, this will go out. So why this bond pair is coming? Because HSO4 minus can form a bond with the silyl. So that is the reason this bond pair is coming out, this is going out. So that is how an olefin is obtained. I think you can observe carefully this olefin. So this is H and this is propyl group. This is propyl group, this is H. What it means? The propyl groups are in opposite direction. So that means this is E. E means trans. What it means? It means that this reaction is a stereospecific. How it is stereospecific? That I will explain in the next slide. So here, what you can observe, just observe the what is that? Peterson olefination. How the olefin is formed. This is alpha carbon, this is beta hydroxy. That means beta hydroxy containing silyl compound undergo elimination in presence of H plus. Here H2SO4 will act as a source of H plus. So that there will be a bond formation between this oxygen and H plus. That is how hydronium ion is obtained. So once there is a formation of hydronium ion, this bond pair is try to move towards oxygen. When this bond pair is try to move towards this, then HSO4 minus can form a bond with the silicon. That time this bond pair is coming over here. So that is how olefin is obtained. So here the olefin, what you can observe that the propyl groups are on the same side. If the bulky groups are on the same side, it's called Z. It's also called as a cis. So this is about the Peterson olefination. But here I'm mentioning that stereospecific. How it is stereospecific? So that I am going to explain in the next slide. So look here. So this will be the staggered form. This will be the eclipsed form. Same moiety I am taking in a eclipsed form. So here what you are observing, this is a silyl compound. And this carbon is a beta carbon. This carbon is alpha because silyl is the prime importance. Because of why we are giving silyl as importance? Because the atomic number of silicon is more compared to the carbons or oxygens. So that is the reason this is alpha carbon, this is beta carbon. So I am taking the eclipsed one. Eclipsed in the sense you can observe that this is the front carbon and this will be the back carbon. Okay. So that means this group is exactly backside of this group hydroxy is there. Exactly backside of this propyl group, another propyl group is there. Okay. So what will happen here? This eclipsed form in presence of base I am taking. In presence of base, so what will happen? There will be a anion formation. How the anion? O can react with the O minus. O minus is forming. How the O minus is forming? K plus is potassium hydride. H minus is available. H minus picks up this proton. So going out as a H2 is a gas. Then there will be a new bond formation between the oxygen and between the potash. So, okay, what will happen? What will happen? Right, anion formation like this. This anion form a bond with silicon. So it will form a compound like this. At this time, this bond pair coming over here, this bond pair goes over here and form an alkene. So because of the alkene, here the formed one is cis. And this is the mechanism. This mechanism in presence of base. Okay. So that means in the base catalyzed olefination, only the cis is forming. So in the acid catalyzed, it is possible to get two cis as well as the trans. Overall, what we can say that olefination is a stereospecific reaction based on the reactant or the substrate. So with this, I will take one more example. Okay, so that is this. So you know that silyl, this is a silyl compound, and this is a carboxylic ester one, and here this is active methylene group. So active methylene group means acidic proton is available. Acidic proton means what will happen? There will be a new, this proton is captured by a base. So this is also a base catalyzed one. So there will be an anion formation. Suppose during this reaction, if there is a presence of aldehyde, so what it will do? There will be a new bond formation between this carbon and this oxygen. So a compound obtained like this. So what will, so here what is happening? This oxygen form a bond with silicon. This bond pair is going over here. So that's what I have shown here. So this oxygen form a bond with silicon. This bond pair is going over here. So that is how a product is obtained like this. So here, based on the R group, so we can say that cis or trans. And the one more thing, I think you are aware about the TMS, trimethylsilane. Trimethylsilane is widely used as a protecting group. It is also used in the organic synthesis. It is also used in, more particularly as a solvent in NMR. Okay. I think you are observed that the extreme right peak in NMR, you can find this peak, TMS peak, internal as an internal standard. TMS will be used as an internal standard. This is about what is called as silyl, organosilyl compounds. So today we discussed about the importance of the silyl compounds, more particularly the bond energies. The bond formation between the oxygen and silyl and fluoride is more because of strong bond formation. Because of this aspect, it finds application in organic synthesis. So that is the reason we also discussed about the reactions, preparations, and also reactions. So reactions, more particularly, what happens when triethylsilyl halide when it is treated with ether, epoxide, okay, esters, okay, and then what is called as carbamates, and also we discussed about what happens more particularly olefination reactions, double bond olefin bond formation. This is about what is called as organosilicons. So up to this, if you have any doubt, you can ask. If there are no doubt means you can log out.